Good afternoon, everyone, and welcome to the SaferSim webinar series. SaferSim is a Tier 1 university transportation center funded under the FAST Act with a focus on promoting safety. Today will be the first webinar featuring research from the 2016 center. The presentation will be 30 minutes long, and there will be time immediately after for questions or discussion. Feel free to use the chat box if you have any comments. I'm pleased to welcome our presenters from the University of Iowa, John Gaspar and Chris Schwarz. I'm going to mute.
Okay. Good afternoon, everybody. Hopefully everyone can hear us. We're excited to have the chance this afternoon to talk about some of our recently completed research on using driver state detection in automated driving. This is John Gaspar speaking right now. Chris Schwarz will jump in here in a minute. Omid Kashef, our graduate student on the project, who really should be credited for doing a bulk of the work, won't be here today. He has a class conflict, but for those in the SaferSim community, I'm sure you'll see him around at the upcoming symposium in Massachusetts. Before we get started, we want to just kind of give a quick shout out to some of the many folks who've contributed to this research. We'd like to thank SaferSim as well as AISIN Technical Center of America for supporting the work you're going to hear about this afternoon. You can see some folks on the left from the National Advanced Driving Simulator who should be credited for doing a lot of the really hard work involved here. And then folks from AISIN on the right, we want to thank them for their guidance and their support throughout the project. Okay, so we want to kind of start, I think, where a lot of people begin when they talk about automation with the SAE levels. And there's been a lot of talk in the recent last few years about kind of the transition from lower levels of automation, these kind of driver assistance systems, to higher levels. And what we're going to talk about today are some of these challenges in higher levels and how we might be able to address them using driver monitoring. So the real challenge as we transition to kind of partial or conditional automation is that the driver can be really pretty far removed from the control loop, but is still expected, as you can see here in the third column, to be kind of the fallback in a situation where automation were to fail. I think a really telling example of this is the Williston, Florida Tesla crash. So for those unfamiliar, I really suggest going back to read the NTSB report because I think it's really an interesting case study in automation. But essentially what happened is a Tesla was approaching this intersection and a truck was turning at the same time. The Tesla failed to detect the truck and basically ran underneath and sheared the top off the vehicle. But what's really interesting about this from a human factors perspective is that there's some pretty good indications that the driver wasn't very attentive in the many minutes leading up to this crash. So when they go back and they look at hands on wheel time, for instance, out of the about 40 minutes the driver had been driving, it was like less than a minute that the driver had their hands on the wheel, which is pretty suggestive that the driver was not very engaged in the driving task. And I think for today's discussion, this really points to a potential role for driver monitoring. As vehicles become more automated and drivers potentially become more disengaged for longer periods of time. The idea of driver monitoring isn't necessarily new. A lot of vehicles have done this for many years using things like lane position, vehicle performance, driver inputs through steering. We're going to talk today about driver monitoring using a vision-based, a camera-based system, which you can see here on the right. And I think that really has some advantages as we move into higher levels of automation, particularly as the signals we get from the driver become fewer and fewer. And really, we want to kind of begin the discussion today by talking about how a driver's state can and should be used in the context of automation. I think that's where we kind of started this project from. And we can think of it being used in many different cases, which we can categorize, I think, in a couple of ways. So if we look at kind of the idea of keeping the driver in the loop during periods of nominal driving, so these are situations where the automation is working. The driver is just kind of sitting back, letting the automation do its thing. But like I said, because the driver is expected to be the fallback to take kind of control for the automation in situations where it fails or where it misses something, driver monitoring can be used to kind of keep the driver engaged. The other situation where driver monitoring might be useful is in the case of takeover, and that's kind of what I've just been talking about, situations where we need to get the driver back into the loop quickly. And we're going to talk today about how we might be able to use driver monitoring in that situation specifically. So here you can see our kind of two major research questions that we'll address today and that we addressed in the project. The first was whether we can use driver monitoring to keep drivers situationally aware of what's happening in the driving scene, basically keep them in the loop. And then we wanted to see whether that translates to performance in situations where the automation fails. And then the second bullet here, the second research question was basically, can we use driver monitoring to augment the way that we're handling takeover? So if we know that a driver's impaired in some way, can we use information about their state to modify that process? So we'll give some background on the study design and then get into the results. So we had a design with 24 or 23 drivers who all were licensed, all kind of younger to middle-aged. They drove an automated vehicle drive that we've been using in our simulator for several studies now. So this builds on previous automated vehicle work through SaferSim. But very briefly, this was a 40-minute drive where drivers were driving with a system meant to mimic a level 3 automated vehicle. While they were driving, they were encouraged to perform this engaging secondary tasks. So what this was it was a trivia game on an iPad. So we gave them an iPad and they could pick kind of a category, and basically what they did, like you can see here on the right, was to answer trivia questions. And we incentivized them to engage in this task by basically telling them that they'd get more money if they answered more questions. So there was some incentive to kind of keep engaging with the task when they could. And I think overall we found that this was a pretty good way to get drivers to disengage from the task, to look down at that secondary task display. So throughout the drive, as we've done in previous studies, we kind of interspersed some takeover situations. And we'll talk about two of those situations here. So we kind of categorize them by whether the automation would have known that it was going to have to hand off control to the driver prior to the situation. So dropouts are essentially situations where the automation just suddenly failed and kind of suddenly handed back control to the driver. And then handoffs were situations where drivers had a takeover request several seconds before they encountered the event. So in this case, we're talking about approaching a work zone. I'll show examples here, so hopefully these play. So here what you're going to see is a dropout event. So this is an event where the driver is coming around the curve and the automation essentially kind of loses tracking on that curve and begins to drift out of the lane. And the point of failure, you'll see here she receives a takeover request and has to retake control of the vehicle. And then I'll show an example of a handoff situation. So here, like I said, she's going to approach a work zone with some cones and some construction workers. And she's going to get a takeover request, I believe, 7 seconds preceding that work zone. Okay, so one thing that's worth noting at the beginning of that clip is that she's just engaged in that secondary task, and I think that's pretty typical of what we saw. So people were pretty willing after a few minutes to kind of cede driving to the automated system and to pick up that iPad and start doing those trivia questions. So in addition to and I saw a question about the takeover request. I'll go ahead and answer that quickly because I think it's important. So all of those takeover requests, you can hear the auditory component, but there's also a visual component that's appearing on the instrument cluster, as you can see here. And I believe I've got an example of what that takeover request looks like in a slide or two. So in addition to kind of looking at those takeover situations, we also wanted to understand the impact of the ways in which we're using driver monitoring on situation awareness, so how aware drivers are of their surroundings at any given point in time. And really a large part of the problem or potential problem with automation is that drivers are going to be out of the loop and kind of lose an awareness of what's happening around them, which then impairs their ability to kind of retake control quickly. So we used kind of a classic situation awareness measurement technique where we basically blanked out the screens of our simulator and we asked drivers where vehicles were positioned around them. So we used just a simple answer sheet like you can see here, and drivers basically just had to indicate the position of the vehicles that were around them at the time where we froze everything out. So here's an example of what that looked like. And drivers were trained to do this, so they knew that these were going to happen. They didn't know when they would happen, but they knew that they would have to do this at different times throughout the drive. So you can see here that she's filling that out. So I'm going to pass things to Chris Schwarz for a couple slides here, who's going to talk about our driver monitoring approach and what we used to classify whether drivers were impaired or not.
Thanks, John. So I'm just going to be with you for a couple slides here while I go through this, and then I'll hand it back to John to go through the results. But when we think of implementing a driver monitoring system in the context of automation, we need to, first of all, provide some method of detecting the driver's state or attention. And in this case, we're using a driver monitoring system from AISIN. That's a production-ready unit that we installed in the car. And then the job was to use the signals that that unit could provide to classify the driver's attention. And I will describe that in some more detail in, I think, the next slide or two. And then finally, what do you do with that information once you get some sort of classification? In our study, we presented an attention alert to the driver that it showed up as a message that said, look forward. And then the blue part in the center of that graphic on the right is actually just the state of the automation. It indicates that the automation is on. And then there was a white ring that you can see in the graphic that showed up around that blue graphic. So the white ring plus the look forward message were indicators to the driver, in addition to an audio component to look up. And that alert is different than the takeover request that you heard in the previous in the video. So as I mentioned, the AISIN DMS that we used here is a production-ready unit that could you might see in a car on the road, and it provides a bunch of different signals related to eye gaze, signals related to face orientation, signals related to eye closure, that type of thing. It's located above the steering wheel, back by the instrument cluster, circled by the yellow ring there is the location. So it was looking a little bit up at the driver through the steering wheel, and it gives a perspective of the driver's face that you can see on the right there. So in terms of coming up with some algorithm or classifier for attention, we did try to do the about the simplest thing that we could so that it would be robust. And one of the reasons we could do that was that we weren't testing a wide range of behaviors in this study. You kind of saw what was happening in the video, where the driver's face would be up, pointed at the road, or down, pointed at the tablet. And that was pretty much the two things that happened. So that made things a lot easier, and it allowed us to simplify an algorithm that we would come up with. And something that would go into a real car on the road would obviously have to take into account a lot of different types of behaviors. But what we did was defined an elliptical region in the forward scene. And this is something, if you're familiar with the measure called percent road center that Trent Victor has used for several years, it's what happens in that algorithm as well. So you define an area that is looking forward, and everything else is not looking forward, basically. But what you have to do, because every driver is a different height, and every driver has a slightly different resting position in the car, is you have to calibrate this region for each driver. And we did that in the beginning of each drive. As they were driving manually, they would get up to speed, and they had to drive for a little while before they would put it into automation. And so during that time, you can measure what the angles are that the DMS is measuring as the driver is just looking at the road and driving. And you can make a two-dimensional histogram from that, and it makes a very nice picture of what the most common point of gaze is, and with a distribution around it. So that becomes the nominal forward-looking position, and around which you build your ellipse. And then the algorithm is very simple. We just start to increment a counter whenever the driver's face is pointed outside of that region, and it increments at 1 second every second. So it's just ramps up over time, and then we cap it at 60 seconds. Can't go above that. And then when the driver looks back at the forward scene and they're within the ellipse, then we start to decrement that counter and let it fall. But we let it fall much more quickly, about 10 times the rate that it climbed. So it could fall back to zero fairly quickly. And then throughout the scenario where we put in conditions to test the attention and trigger an attention alert, we will activate the alert whenever that counter is greater than 30 seconds. So that means if the driver has been looking away from the forward scene for at least 30 seconds, and we're in a condition that supports an attention alert, then we would trigger it at that time. All right, I'm going to turn it back over to John now.
Okay, so very quickly, I'll talk about how we use that from an interface perspective. So we're essentially comparing two different conditions against a control group. So our control group looks just like the examples I showed. When we're not using driver state information in any way, we're just giving them a takeover request 7 seconds in advance of these events. So our attentional maintenance condition is really kind of what Chris was just describing. So this is the idea that throughout the drive, we're giving those attentional maintenance warnings to the driver when they've been looking away. But we're not modifying the takeover process in any fashion. So we're giving them these attentional alerts throughout the drive, and takeover looks just the same. And our third group is the state-contingent takeover group. So the idea here was to not modify the way we're handling attention throughout the drive, so we let them disengage just like the control group. But what we did was we used the driver state information in the takeover event. So essentially what we did was we looked for whether drivers were classified as distracted leading up to when we were going to issue the takeover message. And if we noticed that they were distracted, we added some additional time. So 3 seconds in advance of that takeover request, we gave them kind of that same attention alert. And the idea was that we could kind of give distracted drivers a little bit of extra time to get back into the loop before they needed to respond. So I'm going to show examples of what each of those look like here. So this is our attentional maintenance group. So you're going to see here that she's going to receive those messages as she's looking away. And maybe she didn't. Maybe that was the wrong clip. But the idea was that she would get those kind of reminders up on the instrument cluster with kind of a chime when she'd been looking away for long periods. I think that cut off prematurely. This is an example of what a state contingent takeover looked like. So here again, you're going to see kind of an earlier message. So that's what our attentional maintenance reminders look like. We kind of get that subtler chime. And then the takeover message, just like all the drivers receive. Okay, so I want to talk first about attentional maintenance. I'll go kind of quick here because we're running a little short on time. So our first question was whether we could enhance situation awareness by providing these kind of attentional alerts throughout the drive based on driver state. So here what you're seeing is percent road center gaze, like Chris was describing. Higher values here indicate the drivers were looking up more of the time than the baseline group, and that's just what you see with this attentional maintenance condition relative to the baseline group. But what's really kind of interesting is if you then look at accuracy in that freeze probe task. So again, that's when we're blanking out the screens and asking where the vehicles were around them. We see this nice bump for the attentional maintenance group in accuracy relative to the baseline group. And what that suggests is that providing these attentional alerts is enhancing drivers' understanding of what's around them. And we think that's because they're just having to look up more often. Okay, so let me talk a little bit about whether that translates to response time in these events. Response time in automation takeover situations is kind of more complicated than in traditional response time tasks because it's kind of this composition of many different processes. So here I'm going to talk about two of those. So one is the time it takes drivers to return their hands to the steering wheel, and we're tying everything to these takeover requests. So hands on steering wheel time, and then the time it takes for drivers to initiate a steering response, kind of a corrective steering maneuver. So if we look first at the dropout events, so again, these are times where the automation just suddenly fails. What we can see here is that we're getting faster reaction times, both in terms of hand reaction time and steering response time for the attentional maintenance group relative to our baseline group. So that suggests that drivers, in addition to having higher situational awareness, are also responding faster. If we look at handoff situations, I've plotted all three of our conditions here. And again, these are kind of more planned out situations where the automation knows that it's going to have to hand back control. The really interesting effect here seems to be for our state contingent group. And you can see here that they're getting their hands back on the wheel much more quickly in certain cases than our other group. So negative values here indicate that they're returning their hands to the steering wheel even before they're getting the takeover request. And I know that I went through that quickly, so we're happy to answer questions on this. But I think in general, the conclusions that we want to draw here, the first is that we see this really interesting effect from providing these attentional maintenance alerts. And that seems to both increase situation awareness and to help during takeover performance, even though we're not changing how that takeover is being handled from a takeover request perspective. I think the interesting gap moving forward here is what happens in the situation where drivers don't get a takeover request at all, this kind of silent failure situation where the automation thinks it's performing fine, but the driver still has to intervene. And that kind of gets back to the Tesla crash that I mentioned at the beginning. The second takeaway, I think, is that there seems to be some benefit from providing this state contingent takeover request information, but that really, I think there's challenges in implementing that sort of system in that it requires that the vehicle be able to sense what's happening up ahead. So it has to know that something's happening up ahead, and it has to know that with enough time to kind of modify the takeover process to give the distracted driver more time. So there does seem to be some benefit, but I think from an implementation perspective, there's also some challenges in terms of modifying takeover. Okay, so I am happy, we're happy to answer any questions. Thank you everyone for listening this afternoon. Jacob, I don't know, do you
Yeah,
want to jump back in?
I can go ahead and read. We have a question that came in. Let's see. So the first question, were there major differences among participants for the engagement in secondary trivia task? There's a comment, it's challenging to get people really engaged and realistically distracted.
I think we were, could you read the first part of that question again? Sorry.
So the question is, were there major differences among participants for the engagement in secondary trivia tasks?
I think overall, we were pretty successful in getting people to engage with that secondary task. I think the incentive structure we had helped with that. I think people were pretty motivated. You could hear in that one video clip that the driver was reporting their score back. Whether or not that's an accurate reflection of how disengaged people are going to be in automated vehicles, I think is an important kind of remaining question. I think we have some recent naturalistic data that suggests that drivers driving like a level 2 vehicle might disengage for like 5 to 10 seconds at a time. I think the disengagement we saw in this study was much longer than that for certain sequences, which is part of the reason we use that 30-second threshold.
Thank you, John. We have another comment that came in, and Charles Green mentioned data on takeover with silent failure available in Linares 2017 at TRB that included distraction task and was an in-vehicle on-track study. So that's just some information for you.
Okay, yeah, that's great. Yeah, I think there seems to be more and more studies that are looking at that situation, and I think that's a really important one because that seems to be where a lot of the crashes have been happening, is kind of those silent failure type settings.
Excellent. Another comment came in about good distraction techniques in FHWA study, also reported by Linares 2013. And excuse me on the pronunciation, I'm not sure if I'm saying that name right, but that was at Driving Attention. Um, so I'll be sure to I can share those with you, John, afterwards. Make sure you.
Yeah, that's great. Thank you for the suggestions.
Yeah, so we do have time for a few more questions, if anyone has anything they'd like to add. I will mention that we did record this webinar, so we will get it up, we'll get it edited and posted on our YouTube channel, hopefully before the end of the week. We'll also send out the link to that recorded webinar to all the registrants. So if you're in this meeting room, you'll likely get that link to the webinar. Okay, well, it looks like that is everything. I know John does have his email down there at the bottom if anyone would like to follow up with him specifically on any questions. Um, but with that, I guess thank you all for coming, and we will see you at our next webinar. Thank you.
Thank you.
Thank you.